Welcome to the course on two-dimensional signal processing principles and practices. We have done 1D FFT of decimation in time and decimation in frequency algorithms, and we have seen that how the computational complexity getting reduced. Also, the number of stages depends on n, the number of samples you consider. For 8-point DFT, we had taken 3 stages and number of butterflies, and each butterfly computational complexity like complex multiplication and complex addition. Now, without 1D FFT, it is very difficult to comprehend the 2D FFT, though we will be doing that 2D DFT first, and then using one-dimensional DFT, that is row column decomposition method. After that, we would see that how the 2D FFT can be used in this. So, taking the 2D FFT, as we know that the computational complexity is less and it is more efficient algorithm compared to the DFT, and then the computational complexity, if we take order n square in the case of DFT, and it is order n log n in 1D FFT. That is very much useful in real-time signal processing. Also, it reduces the computational complexity compared to direct 2D DFT. If we use this 1D instead of 1D DFT, if we use 1D FFT in computation of 2D DFT, or computing this 2D DFT directly. So, there is a difference between these two. So, it reduces the computational complexity, and implementation also is faster in this case. So, the savings, it offers a computational saving over the direct computation of DFT in either in 1D or 2D. So, getting into the 2D FFT row column decomposition, how this 2D FFT is done. Especially first we will discuss about this row column decomposition using DFT, and then the same thing can be extended to the FFT as well. So, now we take this complex sequence, that is n cross 1, n cross 2, x of n1 comma n2, that is having a 0 outside this interval, that is the region of support n1 between 0 and n1 minus 1, and n2 between 0 and n2 minus 1. So, if the signal exists, x of n1 comma n2 exists only in this region, outside this region, that is 0. So, just the signal size or the image or the 2D signal size is n cross n, which is n1 and n2. And if first we consider the terms of DFT, and then the same thing can be extended to the FFT what we had discussed in DIT and DIF algorithm. So, DFT equation for 2D DFT, you know that x of n1 comma n2, the extended version of 1D DFT is this. Summation varying from 0 to n1 minus 1 and 0 to n2 minus 1, the two-dimensional sequence, and we get the frequency components x of k1 comma k2 as an outcome. Now, taking this DFT equation, for what is the computational complexity here? For computation of 1k, that is either k1 or k2, especially what we had done in 1D, if we just recall 1D DFT, there are the multiplication for complex multiplications were n, and it should be done for n k values, n bind indices. So, it is n square, n into n square multiplication, and the addition is n minus 1 additions for 1 k value, and so for n such k values, it is n into n minus 1 additions. So, now in this case in 2D, we extend the same idea of computing it for n1 minus n2, this n becomes n1 n2 minus 1, and this n here n1 n2, that is square multiplications. So, n1 n2 square and n1 n2 minus 1 additions. So, if we do the same for all k values, then n1 n2 minus 1 into n2 n2 rows here, especially first we will do the row wise computation and then column wise computation. So, for example, if we take row wise computation of 1D DFT first, then n1 n2 minus 1, and such that should be done for n2 rows. So, that n1 n2 square minus n2. So, this is a small number compared to these things, so which can be neglected. Similarly, n1 n2 multiplications, and that should be done for n2 such rows. So, n1 n2 square multiplications you would get. So, now the case of row wise this computation is this. How do we do the row wise computation? So, this can be further extended to column wise computation also. So, a similar idea of row wise computation of one 1D will be 1D in two-dimensional case, and it will be extended. Next, the row-wise computation, if we take the first one, and x of k1 comma k2, this is the DFT equation, in which what we do is just take this portion of it. I mean, that is summation n1 varying from 0 to n1 minus 1, and take this particular summation where x1, n1 and n2 and minus j2 pi k n1 n1. This is a one-dimensional for fixed value of n2. That is, n2 is fixed, or n2 is 0 initially. This is called n2 is 0 first, then it would give a 1D DFT of n1 point DFT. So that can be, we get as k1, that is frequency component here, that is the intermediate signal which you get it after the one row-wise decomposition or row-wise computation of 1D DFT of n1 point. So the n2 is fixed. So n2 is varied 0, 1, 2, 3 like that for each row. Here for n2 equal to 0, this is computed, and similarly n2 equal to 1 and 2, 3 and all the rows of this one, the 1D DFT is computed. So then what the intermediate signal we get is f of k1 comma n2, and using that first the step is f k1 comma n2, compute it from x of n1 comma n2, the signal given, and then do the column wise computation using the intermediate step signal what we get here. Get the x of k1 comma k2, that is from f of k1 comma n2. So how do we do this thing? So that is row of x of n1 comma n2, that is row wise we take it, making this n2 0. So that would taking 1D n1 point DFT, that is making n2 0, you would get with respect to n1. Each value of this is computed. Let us see that through the diagram. Here this is the sequence x of n1 comma n2. So this is the samples are in the region of support n1 minus 1 in this direction and n2 minus 1 in this direction. So we have this type of sequence is called x of n1 comma n2. So what we do, this take 1D n1 point DFT, that n1 here number of samples in this way, suppose it is 8 point in this direction, and if you take the very first row of that, n2 equal to 0, after that n2 equal to 1, n2 2, 3, 4 and so on. So first we will take the DFT of this sample, 1D n1 point DFT. This is the size is depending on n1. So and getting the, so if we just take that, you would get as 1D DFT output, which is in k1, that is only k1, f of k1 comma n2. For an n2 first row is 0, k1 comma 0 will get, that is this row you will get it. So here k1 is 0 here, and then the next one we take the second row, that is a second row, and compute the n1 point DFT and put it over here, that is the second row, and then move to the next row and then get this one. So likewise we can get these rows appended over in the y direction, that is in the n2 direction. So each row will give one row which is of the signals of f of k1 comma n2, where n2 is fixed, that's what they are trying to say, and k1 is given values, every k1 we found that value. This intermediate signal, now this is row wise DFT, that is row wise decomposition or the row wise computation of the DFT, that is n1 point. Next we will take this sequence, second one, that is, and for the case of f of k1 comma n2, k1 equal to 0, then you get k1, that first value, that is going to be a column, one column of f of k1 comma n2, and obtain x of k1 comma k2 for k1 equal to 0, k1 1 and so on. So every column now we have to take, and so x of 0 comma k2 we would get when k1 is 0, that is 1D n2 point DFT. So now we will it should be repeated for n1 columns. So if we take this sequence f of k1 comma n2, the what we had got from that, the row wise one we got it, from that take a column and then compute the 1D n2 point DFT. So these numbers are n2, so n2 point DFT, and then compute this for n2 point x of k1 comma k2 for each column of f of k1 comma n2. So for all n2 values, you need to calculate. So this would give you x of k1. K1 is already obtained. Now we get this k2. So this is the sequence of k1 and k2. This is the 2D DFT of the case we have taken the sequence. So why we are putting this here as a 2D FFT is that we can extend the same concept of row wise and column wise. Instead of performing through DFT, we can do it through FFT also. So take one row wise one row wise in the first case and compute 1D FFT using DIT or DIF algorithm and find the intermediate sequence, that is f of k1 comma n2, and then take the column of it, compute 1D FFT of this column using DIT or DIF algorithm, get the columns of x of k1 comma k2. So this DFT can be simply replaced with FFT algorithm to get this sequence x of k1 comma k2. So that's how the 2D FFT is also done. So the 2D DFT is discussed, and the same way FFT can also be done in this manner. So we get this x of k1 comma k2 for all the columns. So the computation totally, if we take, first one is the row wise computation, second one is the column wise computation. Here row wise we have taken n1 point DFT, and column wise we have taken that n2 point DFT for all n1 rows, L1 columns, sorry, and then here this is for all n2 rows. This is for rows and this is for all columns. Now, what is the computational complexity if we take this n1 n2 minus 1? So that's the additions for first rows, and it should be repeated for n2 rows. Okay, so that's why it is given n2 into n1 n2 minus 1. So we get n1 n2 square minus n2. So approximately this is smaller than these values. So we get n1 n2 square additions. So if we take the multiplication n1 n2, and it should be repeated for n2 rows, so n1 n2 square, that is the multiplication for the row wise. And if you repeat the thing for column wise, so n1 n2 minus 1, and it should be repeated for n1 columns. So n2 n1 square minus n1, which is lesser compared to this, approximately n2 n1 square. So and then n1 into n1 n2, this is multiplication, and it should be repeated for n1 columns, so n2 n1 square. So the multiplications, and if you add all of them, and this additions would be n1 n2 square plus n2 n1 square. So we get, if you take n1 n2 outside, that is, it would result in n2 plus n1. So this is the addition approximately we needed for 2D DFT. 2D DFT, this would be varied for FFT cases. So then if we take the multiplication, similarly adding this one and this one, we get n1 n2 into n2 plus n1. So the multiplication and additions approximately same, because we neglected this, the minus n2 and minus n1 here. So approximately same. This is the number of multiplications required and the number of additions required in the 2D DFT computation of row wise and column wise decomposition. Now if we take this 2D FFT and the comparison or the computational complexity. So direct computation of 2D DFT, if you take, that is n1 n2 can be 5 and 12 or 5 and 12, or we can have it for any number of it, n1 n2 square, right? This is square and n1 square and n2 square. Here that is simply in 1D, it's n square, and this is n square minus n. So that's what that n is neglected here. So n square. So if you extend the same thing to the 2D direct computation, this is the, if you use the formula directly. And if we use the row wise decomposition, we got it n1 n2 into n1 plus n2, and additions also approximately the same. We have neglected a small number here. So that's a complete saving also. And the row column decomposition using 1D FFT, if we extend the same to the FFT, that is 1D row wise FFT and 1D column wise FFT, either DIT or DIF algorithm. So if you see that multiplications here, that is going to be n1 n2 by 2 log base to n1 n2 and n1 n2 log base to n1 n2. So that would be remain mostly same here as well. So this is a big saving in the computational complexity using the row wise and column wise instead of the direct computation. So now how to perform this 2D DFT, what we had learned through row wise and column wise. Let's see that. So taking a small signal of x of n1 comma n2 of 2 cross 2. So 1, 2, 3, 4, these are the samples, and direct computation we will do after that, row wise and column wise computation also. So if you take the 2D DFT equation, that is the extension of 1D DFT, there is two summations of n1 and n2 varying from n1 minus 1 and n2 minus 1. This is the sequence, 2D sequence, and you can see the basis functions minus j2 by k1 n1 by n1, j2 k2 n2 by n1, and this is valid between k1 from 0 to n1 to n minus 1 and k2 from 0 to n2 minus 1, 0 otherwise this one. So if you take that here 0 0, so if you compute first k1 0 and k2 0, so the two terms over here, e power terms, will become 1. So x of n1 comma n2 variation, it is 2 cross 2, so n1 and n2 are taking values for 0 and 1 only. So x of 0 0 0 0 1 1 0 1 1, so adding all of them would result in 1. So x of 0 comma 0, that is x of k1 k2 k1 0 k2 0 is 10. So substituting that equation, again these are summations for 0, k1 is 0, so the other term gets 1, and so we get k2 is 1, so minus 2 pi n2 2. So taking n1 n2 variation over summation, it results in minus 4. The summation results in minus 4, and similarly x of 1 comma 0, which is e power minus j2 pi n1 here, so because k2 is becoming 0 here, so it has only k1 component, and k1 is 1 we are calculating, and it results in minus 2. So this is through the directly applying the formula, and 1 1, similarly k1 equal to 1 and k2 equal to 1, so that results in 0. Now if we take k1 and k2 are again bin indices as we did in the 1D DFT, DC, harmonics, fundamental and harmonics. K1 k equal to 0 is DC, k equal to 1 is fundamental, and k equal to 2 is second harmonic, and so on. So similar idea also applicable to the images. If a k1 and k2 we have, k1 varies from 0 to n1 minus n1, and k2 varies from 0 to n2 minus 1. So these combinations of all k1 k2 bin indices we would get. So here 0 0 point, and that is again DC in both the directions, n1 and n2 direction, and the remaining 0 1 1 0 1 1 also fundamental in one direction and fundamental in other direction, fundamental in both the directions. So because 2D signal is also combination of sines and cosines in two directions, actually one in x and y direction. So that's how the image is being interpreted. So when we do the same DFT of 2D DFT of images, then we would interpret the details of bin indices and how it can be, how the frequency components of an image can be extracted from that. Now getting this values, what we got is x of k1 comma k2 is 10 and minus 2, minus 4 and 0. So 0 0, and then we got it here minus 2 and minus 4 and 0 0. This is 1 1 component. Now if we this direct computation can be obtained from the MATLAB code, simple code. X is this 1 2 3 4, and FFT 2 x, the capital X, what we got is FFT 2 of x comma 2 you have to give the size here. 2 is x, and here 2 cross 2 matrix the input is, and 2 cross 2, so x small x of 2 cross 2, and you get the capital X, which is the bin indices of the 2D DFT. So this is the sequence, and what we had got is for a row wise computation, let us see using 1D DFT. That is the direct computation, what we got it, and now using the 1D DFT, the row wise computation, that is 1D n1 point DFT. Take the first row 1 2, so this sequence will be, this sequence is plotted as 1 and 2 3 and 4. This is how this is n1 and n2. So the first row is taken and computed 1D DFT. This is 1D DFT equation, this is familiar now, and x of 0 is 0, n small n is varying from 0 to 1, 0 and 1. So if you take 0, that is finding the DC of this is resulting in 3, and bin index 1 gives minus 1. So in this expansion, this is taking the 1D DFT of this one. n1 point DFT, and resulting in 3n minus 1. And similarly, if using the 1D DFT for a second row, this is 3, 4, the second row of the sequence, this sequence now, 3, 4. So 3, 4 if we take, compute this 3 and 4 results in 7, and that is minus 1. That is again for 3, 4 we computed a 1D n1 point DFT each row. So 2 rows were there, 2 such rows were obtained. So these are f of k1 comma n2, that is 3 minus 1 and 7 minus 1. These are the 2 rows of f of k1 comma n2. So now we have to do the column wise DFT on this. So we do the column wise of first column, take the 3, 7 and then compute 1D DFT of n2 point. This is one column and second column. So this n2 also is 2 here, n1 also is 2, so there is no distinction. But suppose if we have the different values of n2, so this is n2 point DFT, that's for the first column. So applying the DFT equation, you get 10, and the second equation which results in minus 4. So second, again for the second column, apply it to the DFT equation. So we get x of 0, x of 1 as minus 2 and 0. So which was the result of x of k1 comma k2, 10, minus 2, minus 4 and 0. We can see the 2D DFT using 1D DFT, that is row wise and column wise decomposition, and the direct computation which results the same x of k1 comma k2. So how do we get this through MATLAB? That is, x is the 1, 2, 3, 4, the sequence, and first to find the f of k1 comma n2. So k1 comma n2 for which take the first row. How do you compute first row? F1. So x of 1 comma colon, 1 comma colon refers to the first row, 1, 2, and the FFT should be taken as 2. Now you notice that this is 1D FFT, not the 2D FFT. FFT2 is the command for the 2D FFT. So here we are performing the 2D using 1D FFT. So FFT x of 1 comma colon 2, this is the n1 point DFT, and similarly do it for the second row as well, 3 and 4, FFT x of 2 comma colon 2. So this is 1D n1 point DFT again with the 2 number, n is 2 and 2. So now append these rows, this is f1 from here and f2 from here. Okay, so this is f is again 2 cross 2, this is nothing but f of k1 comma n2. So after this we have to perform the column wise on this, that is y1 is equal to FFT of f of colon comma 1, which refers to the column, first column of 1D n2 point DFT, and y2 is FFT of f colon comma 2, which is the second column of f of k1 comma 2. So y1, y2, now we get this 2 columns we used to get, and these 2 columns are appended y1 and y2, this is y. So the result what you get is the f1 from here, this one is giving 3 minus 1 and first row, and the second row, that is 3 minus 1 and 7 minus 1 for f of k1 comma n2, and this is 3 minus 1 and 7 minus 1. This is the first step, row wise computation result. And if you take the column wise, y1 and y2, that is okay, taking this column 3, 7 and minus 1 and minus 1, which results in y1 and y2 as this. So which is similar to the result what we got 10, that is the same thing, minus 2, minus 4 and 0. So this is the resultant output. So 2D DFT is performed using the 1D DFT, row wise and then column wise DFT. This is they illustrated with a small piece of 2 by 2 signal, and this can be extended for any size of image also. So the computational saving, as we have discussed, that saving of using this DFT, 1D DFT, but here the computation, actually we are doing it with FFT in the MATLAB code. So but the direct computation we did with the DFT. DIT or DIF algorithm can be used to do the FFT in the 2D DFT computations as well. So with that, we have given the 2D DFT algorithm, that is row wise and column wise computation of 1D and 2D DFTs, how the computational saving can be achieved through this, especially getting the intermediate signal, and then from that intermediate signal again we get, there are 2 steps, we get this final x of k1 comma k2. There are two steps, one is row wise and then another one is a column wise one. So unless until we know the 1D DFT, and this extending to 2D DFT for row wise and column wise, which is very much helpful. Otherwise, you have to go for 2D direct computation, that is using the formula. So that has the computational complexity more compared to row wise and column wise DFT. And further improvement in computational complexity can be achieved through applying 1D DFT also as an 1D FFT, and 1D DFT column wise also as an 1D FFT. So in that way, further reduction in computational complexity could be achieved through this. So this is due to whatever we had done so far, and that how the computation saving can be done through this algorithm for the 2D DFT or 2D FFT, that is a fast Fourier transforms. So the example which we had taken for FFT, just take it for a 8-point DFT signal we have already done for 1D DFT, that is having the 1 kHz and 2 kHz sequence, and apply the 1D FFT, and then get the 1D FFT DIT and DIF algorithm outputs, and similar sequence of 2D can be used and FFT can be computed as well. So with this we complete this Fourier analysis, and we will continue with the discrete cosine transform in the next lecture. Thank you.